Many of you have heard the terms nuclear fission and nuclear fusion before. Nuclear fission means the splitting of atomic nuclei. This is the process by which energy is generated in nuclear power plants. With fusion, it is exactly the other way around. Here, the atomic nuclei amalgamate. One result of nuclear fusion shines down on us from the sky. This is the energy that stars like the sun emit. But what exactly happens in these two processes? And why is so much energy released in the course? To be able to understand this, we first have to recap what the structure of an atom looks like. In the center, there is the atomic nucleus. That is to say, the thing that is split, or that amalgamates with another nucleus. Nuclei consist of neutrons and protons. The protons are positively charged. The neutrons have no charge, hence they are neutral. Thus, the atomic nucleus as a whole is positively charged. Around the positively charged atomic nucleus, so-called electrons are whirring around, like in a kind of cloud. They are negatively charged. So now let us look at what happens when nuclear fission takes place. Here, the atomic nucleus is hit by a single neutron that is flying around. The impact causes the atomic nucleus to split into two new nuclei. Each of them takes part of the electrons with it, so that two new atoms are formed. In the case of some very large atoms, a few neutrons are additionally released. When uranium atoms are split in a nuclear power plant, this usually involves the release of 3 neutrons. These can then affect the next fission processes in a chain reaction. And finally, energy is released, and very much of it at that. 1 kilogram of naturally occurring uranium has the energy of 12,000 liters of mineral oil, or of almost 19,000 kilos of hard coal. But where does this energy come from, and why is it so much more than in the case of other energy carriers such as oil and coal? Let us recall, besides the neutrons, the atomic nucleus only consists of the positively charged protons. Now, equal charges repel each other, similar to the equal poles of two magnets. The fact that the protons in the atomic nucleus remain together nevertheless is due to the so-called strong interaction. This is one of the 4 fundamental forces in the universe, and by far the strongest. By the way, this force used to be called nuclear force, or strong nuclear force. It acts like a strong rubber band that holds together the atomic nucleus with its protons, which we know do not really want to hang around so closely together. When the impacting neutron forces the nucleus apart, it is exactly the energy that has been stored in the rubber band that is released. This energy is not released upon the burning of coal or oil. In this case, there are chemical reactions developing in which the atomic nuclei are not touched and where only electrons are exchanged. Nuclear fusion presents a similar picture, or rather, a mirror image. It only works with small atoms, like hydrogen, for example. The atomic nucleus of the latter consists of only 1 proton. If one now tries to force 2 of these protons together, these 2 would have to repel each other due to their equal charge, as in the case of magnets. When talking about atomic nuclei, this is referred to as the so-called Coulomb force. This force acts as if each of our protons had a fence around it, trying to keep off other protons. Like fission needing a force that overcomes the rubber band of strong interaction, fusion also needs one that forces the protons so closely together that the fences are pulled down. And once this happens, and the protons come too closely together, strong interaction comes into play again, and makes sure that the 2 amalgamate into a new atomic nucleus. As in the case of the nuclear fusion on the Sun, it is in fact 4 hydrogen atoms, that means 4 protons, that amalgamate to form a helium atom. But as the latter only has room for 2 protons in its nucleus, the other 2 are released, similar to the excess neutrons upon the fission of uranium. And of course, this also involves the release of a lot of energy, even more than upon nuclear fission. It would only need 1 single gram of fuel, or the hydrogen isotopes deuterium and tritium, to gain as much energy as from 12,000 kilos of hard coal. This is why scientists try to develop power plants in which energy is won from nuclear fission. But how is the Coulomb force, meaning the fences around the protons, overcome? This happens by speeding up the atomic nuclei, and that happens when they are subjected to great heat and/or pressure, The more pressure is available, the less heat is needed. Sooner or later, two atomic nuclei will hit each other at such great speed that the force of the impact will overcome the Coulomb force, and the protons will no longer repel each other. This is also what happens in the Sun, where 15 million degrees and a pressure of 200 million bar are necessary to amalgamate the hydrogen atoms. In a fusion power plant on Earth, we would even need 150 million degrees, as we have a lower pressure than inside the Sun. However, to this day, we have not been able to generate such high pressure in a fusion power plant. If you would like to learn more about this topic, just watch our videos. What actually is radioactivity, or types of radiation?